All right, so want to unlock the secrets of machine learning, but like through this super cool lens of probability.
Sounds awesome.
It is awesome. We're going deep, deep, deep into Kevin P. Murphy's book, Machine Learning, a Probabilistic Perspective. But like, don't worry, we're not going to get lost in the weeds, you know?
Yeah, it can be a dense book.
Totally. We're going to like pull out those core concepts so you can really like grasp them.
It's like having a map and a compass to navigate this like really complex world.
Exactly. So first stop on our journey, the basics, right? Supervised versus unsupervised learning.
Got to start somewhere.
Right. So supervised learning, it's like having a tutor, right? You've got your labeled data, think inputs, like someone's height, their weight.
And then the output you're trying to predict, like maybe their blood pressure, something like that.
Yeah, exactly. So you're learning the mapping inputs to outputs.
Based on those labeled examples.
But here's the thing. Inputs can be way more complex than just numbers.
Oh, yeah.
Think images, sentences, whole emails even.
It's crazy what you can do.
All right, now imagine this. You walk into a room, it's full of puzzle pieces, but there are, like, no instructions.
Oh, that's unsupervised learning.
Bingo. You got the data, but no labels this time.
So it's up to the algorithm to, like, figure it out.
Exactly. Uncover the hidden structure, patterns, all that jazz.
So, like, you're building a model of how likely it is to see certain data points, like density estimation.
Okay, that makes sense.
And it often uses those multivariate models, meaning you're juggling, like, multiple features all at once.
So we've got our two main learning styles, supervised and unsupervised. But to really understand this stuff, we need probability, right?
Absolutely. Probability is like the foundation.
The book lays it all out, those essential concepts. Like, they explain that probability density function, or PF. They use the uniform distribution to explain it.
Oh, yeah, the shape of probability for that, like continuous data.
Right. So imagine, like, every value within a certain range has an equal chance of popping up.
Like rolling a die, each face has the same chance, right?
Exactly.
Yeah.
And then there's standard deviation, which I always struggled with. I don't know about you.
Yeah.
But the book makes it so practical. Like, it's in the same units as the data.
Right. So you immediately understand like how spread out the data is, makes it easier to grasp.
Okay, let's talk discrete distributions.
Those are super important.
For data that comes in those, like, separate values, like flipping a coin 10 times, how many heads you get.
Right. And you could use the binomial distribution for that. That helps model those probabilities.
It's got so many applications, too, beyond coin flips, Think A/B testing in marketing.
Oh, interesting.
Yeah, like testing different versions of a web page, seeing which performs better.
And you can use the binomial distribution to analyze that.
Exactly. See if the difference you're seeing is like real or just random chance. So that's binomial. What about for rare events, like radioactive decay?
Then we've got the Poisson distribution.
The Poisson, perfect for when those events happen infrequently, but like predictably over time. Okay, so now we've got discrete distributions sorted. But then there's this thing, transforming random variables.
Oh, yeah, that can be a bit tricky.
It is. So how do changes in one variable affect another?
Yeah, cause and effect, but, with probability thrown in there.
Always with probability. Okay, so if one variable changes, we can use these transformations to predict how other related variables might change.
Exactly, yeah.
Super useful. Speaking of predictions, the book dives into Monte Carlo estimation.
Ah, yes.
So that's about, like, generating random samples to approximate something, right?
Exactly. Really useful for expectations, especially those complex integrals that are like a nightmare to solve directly. And it ties back to that central limit theorem. The more samples you have, the closer your approximation gets.
More samples, better accuracy. Got it. Okay, get ready for a mind shift. We're entering the world of Bayesian statistics.
Now we're talking.
A whole different way of thinking about probability.
Yeah, in Bayesian inference, we update our beliefs as we get more evidence.
So it's like constantly refining our understanding as we learn more.
Exactly. We start with our prior belief, the prior distribution, then there's the evidence, the likelihood, and then we update that belief based on the evidence, and that's the posterior distribution.
It's a, like, constant learning process. Okay, the book introduces this concept called conjugate priors.
Conjugate priors, yeah.
They sound like a shortcut.
They are. They make the math way easier, and you end up with a posterior that has the same form as the prior.
Nice. So it's simpler, but still accurate.
Exactly. And hey, here's a pro tip. When you're dealing with coin flips, remember the beta distribution.
Okay.
It's the conjugate prior for the Bernoulli likelihood. Makes things much smoother.
I'll keep that in mind. Okay, next up, posterior mean and mode.
Yes. Those are point estimates in Bayesian inference.
So they give us our single best guess, right?
Exactly, for the parameter we care about.
Gotcha. Speaking of cool stuff, let's talk about naive Bayes classifiers.
Simple but surprisingly powerful.
They are. Okay, so they assume that, like, features are independent of each other once you know the class label.
Yeah, like in an email, we assume the words are independent of each other, but only once you know if it's spam or not.
Exactly. That assumption, even though it seems naive, it works really well.
It does, and they're used in spam filters, right?
All the time. Classic example. And the book even gives us this challenge, like, build a spam filter from scratch using the Bernoulli product model.
Cool.
Yeah. And it's not just spam filtering. They go into document classification, too, using similar principles to categorize documents into different topics.
So versatile.
All right, now let's move on to Gaussian models. What's the deal with Gaussian discriminant analysis, or GDA?
Okay, imagine you have data points on a graph, like height and weight, and you want to classify them into groups, male and female, for example.
Yeah, I'm picturing it.
GDA uses Gaussian distributions, those bell curves, to model each group.
So, like, we fit those curves to the data and then use them to predict which group a new point belongs to.
Exactly. And there's this cool connection. If those covariance matrices are diagonal, GDA becomes the same as naive Bayes.
Whoa, it all connects. Okay, what about linear discriminant analysis, or LDA? How is that different?
Well, both LDA and GDA assume that the data follows Gaussian distributions, but LDA, it focuses on finding a projection that maximizes the separation between the classes.
So it's about, like, finding the best perspective to view the data so the groups are as separate as possible?
Exactly. And there's actually a link between LDA and logistic regression, something to explore, maybe later on.
Ooh, intriguing. But for now, let's stick with these Gaussian models and dive deeper into multivariate Gaussians. They're all about modeling, like relationships between multiple variables.
Yeah, let's see how they play out in the machine learning world.
Lead the way. Okay, so we're, like, really getting into these multivariate Gaussians now. They sound kind of, I don't know, intimidating.
Well, they're all about understanding how knowing one variable, like, helps us understand the others.
So it's not just looking at those variables in isolation.
Right. It's about how they interact, influence each other.
Interconnectedness, I like it.
The book actually gives an example with an equation. It shows how knowing one variable, like x2, it can directly impact our understanding of x1.
Oh, interesting. So, like, knowing one thing changes what we know about another.
Exactly. Okay, now there's this thing called the partitioned inverse formula.
That sounds complicated.
It's a bit technical, more of a behind-the-scenes tool.
So, like, we don't have to worry about it too much?
Probably not directly, but it's important for those block matrices, especially with these multivariate Gaussians.
Okay, so it's like the engine under the way. We don't need to be mechanics, but good to know it's there. All right, so the book then talks about inference in jointly Gaussian distributions.
So that's about figuring out the conditional distribution of one set of variables given another set.
Okay, so, like, narrowing our focus.
Yeah, exactly. If we know some variables, what can we say about the rest? And then we encounter the Wishart distribution.
The Wishart, another new one.
So the Wishart distribution, it's a distribution over covariance matrices. Remember, covariance matrices tell us how those variables relate to each other.
Right, right. So when we're doing that Bayesian inference for Gaussian models, we need the Wishart distribution to model the uncertainty in those covariance matrices.
Exactly. Always got to count for uncertainty.
Okay, the book circles back to Bayesian statistics now. This time, it's about something called the marginal likelihood.
The marginal likelihood. It's a pretty important concept, actually.
Okay, why? What does it tell us?
It's like a scorecard for our models.
A scorecard. Interesting.
It represents the probability of seeing our data, under a specific model, but averaged over all possible values of the model's parameters.
So it's like we're comparing different models.
Yeah, and we can see which one best explains the data.
Like a model competition. And marginal likelihood is how we pick the winner.
Exactly. Think back to those coin tosses. Marginal likelihood would help us figure out, like, is the coin fair or biased?
Based on those observed heads and tails. Okay, that makes sense. Now, there's also this thing called the Jeffreys prior.
Jeffreys prior, yeah. It's a type of non-informative prior.
Non-informative, so, like, it doesn't really have an opinion.
Kind of. It's designed to be invariant to reparameterizations, meaning it doesn't favor any specific way of describing those model parameters.
So it lets the data speak for itself.
Precisely. And then there's empirical Bayes.
Empirical Bayes, okay. Is that like a hybrid approach to Bayesian influence?
You could say that instead of just setting those hyperparameters based on our prior beliefs, empirical Bayes, it estimates them from the data.
So we're using the data to guide our choices about those like higher level parameters.
Exactly. Okay, now get ready for a bit of a turn. We're going into decision theory.
Decision theory, okay. How does this fit in with, machine learning?
It's all about connecting those probabilities to actions. You see, our models give us predictions, but those are probabilistic. Decision theory helps us choose what to do given that uncertainty.
So it's like the bridge between predicting and deciding.
You got it. And they talk about the Bayes estimator. It's like a decision rule. Helps us minimize that expected loss, make the best choice, in the long run.
Makes sense. All right, now I see the book's going into frequentist statistics, which seems like a different approach, right, from Bayesian?
Definitely different schools of thought. Frequentist statistics, it focuses on those long-run frequencies of events.
So not updating belief, but more like measuring performance over time.
Exactly. They talk about dominance. One estimator is dominant if it has lower risk for all those parameter values.
So it's like finding the estimator that's always better.
Yeah, no matter what.
Oh.
Leads to the idea of admissible estimators, the ones that aren't dominated by any other.
Okay, so the top performers, statistically speaking.
Exactly. And to estimate that risk, we need practical tools. Remember cross-validation?
Oh, yeah. We split our data, train on some, test on the rest.
And that helps us estimate how well our model will do on new data.
Avoid overfitting, right?
Exactly. And speaking of fitting data, remember logistic regression?
Yeah, we talked about that with naive Bayes, right?
Yep. Logistic regression's a workhorse for binary classification, predicting whether something belongs to one category or the other.
Two options, got to pick one.
And the book talks about that sigmoid function, that shaped curve. It squashes those predictions into probabilities between 0 and 1.
Makes it easy to interpret.
And then the log-loss function, it tells us how well those predicted probabilities match the actual outcomes. And minimizing that log loss, it's actually the same as maximizing the likelihood.
Whoa, there's that connection again.
Right, it all ties together. The book then contrasts confidence intervals with those Bayesian credible intervals.
Okay, so confidence intervals give us that range where we're pretty sure the true value is, while those credible intervals are based on our updated beliefs, right? The posterior distribution.
Exactly. Different ways of thinking about uncertainty. Okay, so are you ready to dive into optimization?
Bring it on. Let's find the best solutions for our learning problems.
All right. Optimization is all about finding those best parameters for our model, given what we're trying to achieve. And the book starts with convex optimization.
Convex, okay. That sounds like a good thing, but why?
Well, with convex optimization, we're guaranteed to find the absolute best solution, the global optimum. Imagine a landscape with just one peak.
Easy to find the top.
Exactly. And it links back to maximum likelihood estimation. If that likelihood function is convex, finding the MLE becomes super easy.
Smooth sailing. All right, now the real world isn't always so smooth, right? What about outliers?
Outliers. Those pesky data points that don't fit the pattern, that's where robust regression comes in.
Makes sense.
Robust regression techniques, they make our models less sensitive to those outliers.
Like a more forgiving system.
Exactly. And then there's Bayesian linear regression.
Oh, yeah, I remember that. It's about incorporating those prior beliefs, right?
You got it. And updating them based on the data, a more nuanced way to handle uncertainty. All right, moving on to generalized linear models, or GLMs.
GLMs, they sound powerful, like a framework for tons of different problems.
They are. And logistic regression, it actually fits within that GLM framework.
Really? I didn't realize that.
They all use a link function to connect that linear predictor to the response variable. And the book mentions Fisher scoring. It's an optimization method, especially useful for those non-Gaussian responses.
Okay, so another one of those behind-the-scenes algorithms that just, makes things work.
You got it. All right, ready to simplify things a bit? Let's talk about dimensionality reduction.
Dimensionality reduction, okay. I'm guessing this is where we get rid of some of those extra features, right?
You got it. When you've got tons of features, it can get overwhelming. Dimensionality reduction helps us find those lower dimensional representations that still capture the essence of the data.
So it's like summarizing a long book, but keeping the most important parts.
Perfect analogy. And of course, we have to talk about principal component analysis, or PCA.
PCA, the superstar. I remember learning about that. And the book talks about how important it is to standardize the data first.
Absolutely. Got to make sure those features are on a level playing field. Otherwise, the ones with larger scales could dominate, even if they're not actually more important.
Fairness for all features. Okay, now there's also probabilistic PCA or PPCA.
PPCA. It brings in like the probabilistic perspective to PCA, allows for uncertainty in that lower dimensional representation.
So it's not just about finding the best representation, but also like knowing how confident we are in it. Makes sense. What about factor analysis?
Factor analysis, it's similar to PCA. It's about finding those underlying factors that explain the correlations between variables. But factor analysis, it's got more flexibility in modeling that noise or error in the data.
Okay, so it's like PCA, but a bit more adaptable. And they even combine factor analysis with those mixture models, right, to create a mixture of factor analyzers.
Exactly. Mixture models let us handle data from like multiple underlying distributions. So this mixture, it can capture more complex relationships.
So we've got a whole toolkit for dimensionality reduction now, each tool with its own special powers. Oh, and they talk about supervised PCA. What's the twist with that one?
Supervised PCA, it brings in information about the target variable, the thing we're trying to predict.
So we're not just reducing dimensions randomly, we're doing it in a way that helps with our prediction task. All right, onto sparse linear models. I think this is where that whole sparsity thing comes back.
You got it. Sparsity, it's about focusing on the important stuff, ignoring the noise. In these models, we're looking for models where many of those coefficients, the weights, are 0.
So it's like simplifying our model, right, by getting rid of all those unimportant features.
Exactly. Okay, and they start with Bayesian variable selection.
Bayesian again. So what's the Bayesian way to do feature selection?
Bayesian variable selection treats feature selection as a problem of inference. We're not just picking features. We're trying to figure out which features should be included in the model.
Like deciding which ones to turn on or off.
Exactly. And to do this, they use something called spike and slab priors.
Spike and slab, okay. What are those all about?
They're a cool way to model sparsity. The spike part, it focuses on 0, encourages those coefficients to be exactly 0 if a feature is irrelevant. And the slab part, it spreads the probability mass around, letting coefficients take on those non-zero values for relevant features.
So it's like a filter, right? It separates the important features from the unimportant ones.
Exactly. And speaking of determining relevance, there's automatic relevance determination, or ARD.
ART, okay. So it's like the model figures out what's important all on its own.
You got it. It learns a separate precision parameter for each weight. It controls how much each feature can, like, contribute.
Smart model. Okay, last one here. Sparse coding. What's that all about?
Sparse coding, it's about finding a sparse representation of the data using a dictionary of basis functions. Like, think of breaking down a complex signal into simpler ones.
So we're representing the data using just a few of those basis functions.
Exactly. More compact, more efficient. All right, let's move on to kernels.
Kernels. They always seem kind of mysterious to me. What's the main idea behind them?
Kernels are a way to work in those high-dimensional feature spaces without actually having to compute those transformations.
So like a shortcut.
Yeah, you could say that. They make it possible to model those complex relationships without getting bogged down in the details.
Okay, I like shortcuts. And the book starts with those radial basis function kernels, or RBF kernels.
RBF kernels, they're popular because they measure similarity based on distance.
So closer points are considered more similar.
Exactly. And they mention the ARD kernel. Remember, AR automatically figures out which input dimensions are relevant.
It's like the kernel has a mind of its own. All right, are you ready for support vector machines?
SVMs, bring them on.
They're supposed to be like really effective for classification, right? But kind of tricky.
They can be. So SVMs, they use kernels to find that optimal decision boundary, separating the data points into different classes.
So like drawing a line between two groups of objects, but in a much higher dimension.
Exactly. And there's this concept of a margin.
A margin, okay.
It's the distance between that decision boundary and the closest data points. Wider margin, better separation, less likely to make mistakes.
So it's like a safety zone. What about the hinge loss function? What does that do?
Hinge loss is designed to be insensitive to outliers, those data points that don't quite fit.
Makes the SVM more robust. All right, I'm ready for something totally different. Gaussian processes.
GPs, they're a whole different way of thinking about modeling functions.
Okay, I'm intrigued. So instead of a model with like fixed parameters, we have a distribution over all possible functions.
Exactly. Infinite possibilities.
Whoa, that's a lot. So how do we pick the right one?
That's where that covariance function comes in. It determines the properties of the functions we're considering.
So like it sets the rules of the game.
You could say that. And, of course, we have GP regression.
Using GPs for prediction, right?
Yep. For a continuous output variable, they handle those nonlinear relationships really well, and they give us uncertainty estimates for our predictions.
So it's like our prediction comes with like built-in error bars.
Exactly. And then there's the GP latent variable model, or GP-LVM.
GP-LVM. Okay, what does that do?
It uses a GP to model that mapping from a lower dimensional space to the higher dimensional one. It lets us find those nonlinear relationships that like PCA might miss.
So it's like a more powerful way to find those hidden patterns. All right, what about adaptive basis function models? Sounds like we're getting even more flexible.
We are. Adaptive basis function models, they use basis functions that are learned from the data.
So instead of being fixed, they can change.
Exactly. And they start with decision trees.
Oh yeah, decision trees. I remember those.
They're super interpretable, easy to understand how they make their predictions.
They're like those flowcharts, right, that guide you through the decision-making process.
Exactly. And then the book talks about ensemble learning, combining multiple predictors to do even better.
The more the merrier, right?
Exactly. It's like getting multiple opinions, to make a better decision.
Like a team of experts.
And they mention bagging and random forests.
Okay, remind me what those are.
So bagging, it creates like multiple versions of the predictor by training on different parts of the data. And random forests, they add even more randomness by only considering a random subset of those features at each step.
So it's like a team of experts, but each one has a slightly different perspective.
Exactly. They also mention boosting.
Boosting, okay. What's that one all about?
Boosting, it's like you combine those weak learners, models that aren't that great on their own, to create this like super learner.
So you go with a bunch of rookies, and they train to become all-stars.
You got it. All right. Are you ready for the stars of the show?
Hit me with it.
Feed-forward neural networks, also known as multi-layer perceptrons, or MLPs.
MLPs, okay. They're inspired by the brain, right?
They are. They use these interconnected neurons to process information. What makes them special is they can learn those really complex relationships between inputs and outputs.
So they can learn almost any pattern.
Pretty much, yeah, given enough data and computing power. And they specifically mention convolutional neural networks, or CNNs.
CNNs, I've heard of those. They're really good for images, right?
They are. CNNs use those convolutional layers that look at the spatial relationships between like nearby pixels.
So they can recognize patterns no matter where they are in the image.
Exactly. All right, switching gears a bit. Ready for Markov and Hidden Markov Models.
Okay. So we're getting into those sequences of data now.
Yep. Things happening in a certain order. And the start with Markov panes. The probability of being in a particular state, it only depends on the previous state.
So like it only remembers the last step.
Exactly. They give the example of web page transitions. The probability of going to a specific page, it might only depend on the page you're on right now.
Makes sense. So what about hidden Markov models?
Okay, so with HMMs, the states themselves are hidden. We don't see them directly. We just see these emissions, signals that depend on the hidden state.
Okay, so we're trying to figure out those hidden states based on what we can observe.
Exactly. And there's this cool example of a dishonest casino. They switch between a fair die and a loaded one, and we just see the rolls. The HMM helps us figure out when those switches happen.
So it's like we're detectives trying to figure out what really happened.
You got it. And there's the forward-backward algorithm.
What does that do?
It helps us calculate the probability of those observations and the posterior distribution over the hidden states. So we figure out the most likely sequence of events.
Cool. All right, let's move on to state space models. Sounds like we're modeling like systems changing over time.
Exactly. We have that hidden state and it changes and we get these noisy measurements of it.
Though like the system's got an internal state that we can't see directly.
Exactly. And they start with the Kalman filter.
The Kalman filter, I've heard of that. It's like a tracking device, right?
Kind of. It's good when those system dynamics are linear and the noise is Gaussian.
So it's for systems that behave predictably.
Yeah, you could say that. But what about when it's not so predictable?
Good question.
Well, that's where the extended Kalman filter, or EKF, comes in.
Extended Kalman filter?
It handles those nonlinear systems. It uses linear approximations.
So like it simplifies things a bit.
Exactly. And then there's switching linear dynamical systems, or SLDS.
SLDS, what are those for?
They model systems that can like switch between different linear dynamics over time, like a system with multiple modes.
So it's a more adaptable model.
You got it. Okay, ready for a different type of graphical model.
Hit me with it.
Undirected graphical models. They're also called Markov random fields, or MRFs.
Okay, so how are those different from the directed ones we talked about before?
Well, those directed ones, like Bayesian networks, they use arrows to show, like, cause and effect. MRFs use undirected edges. They're more about dependencies.
So we know the variables are related, but we don't know who's causing who?
Exactly. And the book explains those Markov properties. They tell us which variables are independent of each other.
Given the values of other variables, right?
Right, and they introduce factor graphs. They're a nice way to visually represent those relationships.
So like a map of how it all fits together.
Yeah, you could say that. And there's loopy belief propagation.
Loopy belief propagation. Try saying that 5 times fast.
I know, right? It's an approximate inference algorithm for those MRFs with cycles in the graph.
Okay, so it's for those more complex networks where exact inference is like too hard.
You got it. All right, ready for another powerful framework.
Always. What's next?
Variational inference. It's a way to approximate those complex distributions, especially in Bayesian inference, where those posterior distributions can be a real pain to work with.
So instead of calculating that exact posterior, we find something close to it.
Exactly. It's like an optimization problem. We try to find the best approximation from a simpler family of distributions.
Finding the best match from a set of, like, easier options. What about the mean field approximation?
Mean field approximation, it assumes that that approximation is fully factored, so each variable is independent.
A big assumption. But it makes things easier.
It does. And then there's variational EM.
Variational EM, okay, what's that one do?
It extends that EM algorithm for those latent variable models where exact inference is just too hard.
So it's like a power-up for the EM algorithm.
You could say that. All right, remember Monte Carlo methods?
Oh yeah, we talked about those with Monte Carlo estimation, generating random samples, right?
Exactly. They're great for when you can't solve a problem directly, so you run a simulation.
Embrace the randomness.
Exactly. And they start with importance sampling. It's for approximating expectations.
Okay, remind me how that works.
So we draw samples from a proposal distribution. It's easier to sample from than the actual distribution we care about.
So like we're being strategic with our samples.
Exactly. And then there's sampling importance resampling, or SIR.
Sir, all right.
It turns those weighted samples from importance sampling into unweighted ones, so they look more like the real distribution.
So we're refining those samples, making them better.
Exactly. Okay, now let's talk about particle filtering.
Particle filtering. I'm imagining like a bunch of particles moving around.
You're not far off. It's a sequential Monte Carlo method. We use it for state estimation.
State estimation meaning?
Like, imagine tracking something that's moving. Its position and velocity change over time. We use those particles to represent what we think about the object's state, and then we update those beliefs based on, what we observe.
So it's like the particles are exploring all those possible states.
Yep. And particle filtering is really useful for those nonlinear, non-Gaussian systems.
Where the common filter wouldn't work so well. Got it. Okay, what about Markov chain Monte Carlo methods?
MCMC, those are powerful tools. They're for generating samples from those complex distributions, especially those posterior distributions in Bayesian inference.
Right, those could be tricky.
They are. MCMC methods, they create a Markov chain that eventually gets to that target distribution.
So it's like a random walk that explores all the important parts.
Exactly. And they start with the Metropolis-Hastings algorithm.
Metropolis-Hastings, all right. Sounds fancy.
It's all about proposing new steps in the chain and then accepting or rejecting them.
So like a controlled random walk.
Yep. And then there's Gibbs sampling.
Gibbs sampling.
It's a type of Metropolis-Hastings, but it uses the full conditional distribution of each variable.
Okay, so it's a bit more structured.
You could say that. All right, ready to shift gears again?
Bring it on.
Clustering.
Clustering, that's about like grouping things together, right? Based on how similar they are.
Exactly. We find those natural groupings in the data.
So like sorting things into different boxes.
And they start with k-means clustering.
Oh yeah, k-means, that's a classic.
It is. So you want to divide the data into k clusters.
K being the number of clusters, right?
Each cluster has a centroid, the average of all the points in that cluster.
So like the center of gravity for that group.
Exactly. And each data point is assigned to the cluster with the closest centroid.
Makes sense. All right, what about Gaussian mixture models?
GMMs. They bring that probabilistic perspective to clustering.
So we're using those Gaussian distributions again.
Yep. Each cluster is represented by a Gaussian, and each point has a probability of belonging to each cluster.
Based on how well it fits that Gaussian. Got it. What about hierarchical clustering?
Hierarchical clustering, it builds a tree structure of those
The
clusters.
tree, interesting.
Yeah, so it can be agglomerative, starting with individual points as clusters and then merging them, or divisive, starting with one big cluster and then like splitting it up.
So it shows how the clusters relate to each other at different levels.
Exactly. And they mention Bayesian hierarchical clustering. It does, yeah, Bayesian hierarchical clustering. It's like it brings in that uncertainty to those cluster assignments.
Makes sense. Instead of being so definite, it's more like probabilities, right?
Exactly. It's more robust, more nuanced, especially with that noisy data, or when those clusters overlap a bit.
Yeah, more realistic. Okay, let's switch gears completely. I'm ready to dive into learning Bayesian networks.
Okay.
We've talked about them, but how do we actually learn their structure from data? Sounds tricky.
It can be, yeah. Learning the structure of those Bayesian networks, those directed graphs with the causal relationships, it's a tough problem. The book starts with learning tree structures, which are a bit simpler than those general directed acyclic graphs.
DAGs.
Right, DAGs. So we start simple, build up our understanding.
Okay, so what makes those tree structures easier to learn?
Well, they have a very specific set of connections, right, between variables. So the search space is much smaller, makes things more efficient. There are even some really neat algorithms like that, Chow-Liu algorithm, that can efficiently find the best tree structure.
So it's a more manageable problem, but what about those more general DAG structures? They seem way more flexible.
They are, but that flexibility makes learning much harder. They're like tons of possible DAGs for a set of variables. And then there's Markov equivalence, where multiple DAGs can represent the same conditional independence relationships. It's tough to find the one true DAG that reflects that underlying causal structure.
So it's like a puzzle with like way too many pieces, and some of them might even be the same. Okay, so how do we even begin to tackle this?
Well, researchers have come up with some pretty clever algorithms. They search through all those possible DAGs and try to find the best one that fits the data well but isn't too complex. It's a really active area of research, always new methods being developed.
That's cool. So what about learning Bayesian networks with those latent variables? The hidden ones we can't see.
Oh, latent variables, they definitely make things trickier. Now we have to learn the structure and infer the values of those hidden variables.
So it's like we have missing pieces and we don't know what the puzzle's supposed to look like.
Exactly. The book talks about how we need these iterative algorithms. They go back and forth between estimating the structure and inferring those hidden values. It's a lot of computation, but it's super important for those real-world problems, where we don't always have all the information.
Okay, so it's more complex, but totally necessary. The book also mentions learning undirected Gaussian graphical models. What are those all about?
They use those undirected graphs, right, to show the dependencies between variables, and they assume those variables follow Gaussian distributions. They're really good for those continuous variables like temperature or gene expression levels. But learning their structure, it's a challenge.
Why is that?
That likelihood function, the one that tells us how well the model fits the data, it doesn't break down nicely. So we can't really separate the problem into smaller chunks.
So it's all tangled up.
Pretty much we need special techniques like lasso regression or graphical lasso. They encourage sparsity in the structure, so a lot of those connections between variables are zero.
So it simplifies the model.
Exactly. Makes it easier to understand. All right, are you ready for some wordplay?
Bring it on. I love wordplay.
Probabilistic topic models.
Topic models. Okay, I've heard of those. They're all about finding those like hidden topics in text, right?
You got it. Like imagine an algorithm that can read through a ton of documents and tell you what they're all about, what the main themes are.
That's so cool. I bet it's used everywhere.
It is. News articles, customer reviews, scientific papers, and the book introduces latent Dirichlet allocation, or LDA.
LDA, yeah. That one rings a bell. What makes it so special?
Okay, so LDA, it's a generative model. It assumes those documents are created through a specific process. In LDA, each document is like a mixture of different topics, and each topic has its own distribution over words.
So it's like each document is talking about a few different things at once.
Exactly. And those different things, those topics, they have their own vocabulary.
Okay, I'm with you. So how do we actually use LDA?
Well, we need to train it on a bunch of documents to learn those topic distributions and those word distributions. And remember those inference methods we talked about, like Gibbs sampling. They come in handy here. They help us estimate all those distributions, figure out those hidden themes and their vocabulary.
So LDA is like a code breaker for text. It tells us what the documents are really talking about. So what can we do with a trained LDA model?
Lots of things. We can take a new document and figure out its topics, automatically tag it. We can also find documents that are similar based on their topics. And in recommendation systems, LDA can help us suggest documents that a user might like.
So many applications. It's amazing what we can do with this probabilistic approach, uncover those hidden meanings in text. And the book mentions some even more advanced topic models, right?
It does. There are correlated topic models. They allow for like relationships between the topics. Some topics are more likely to appear together, you know. And then there are dynamic topic models. They capture how those topics change over time.
So topics aren't just these static things. They evolve and interact. Wow, we've covered so much ground today. It's been a really, really deep dive into machine learning, a probabilistic perspective.
It has. We went from the basics of probability all the way to those really sophisticated models like Gaussian processes, hidden Markov models, and these topic models.
I'm feeling inspired, but also like, whoa, there's so much to learn.
There is, but the key takeaway is that probability, it helps us understand why these algorithms work. It gives us the intuition to really grasp machine learning.
Exactly. We've got a solid foundation now. Thanks so much for joining us on this deep dive, everyone. We hope you've enjoyed exploring this incredible world where probability and machine learning meet.
It's been a pleasure.
Keep learning, keep questioning, and keep diving deep into the world of machine learning.
Until next time, TSE Oba.